Okay, so very good morning to everyone. Hope it is audible. Okay, so in today's class, we will be discussing about variable mass system. Okay? Variable mass system. Okay? Now, what is a variable mass system? As the name suggests, the mass will keep varying. Okay? So, what are the forces acting over here? For example, if a rocket lifts off, right? Some force is acting on the rocket because of the gases which are moving out, right? So what are those forces? We'll call that force as thrust force. Right? Okay. So let's consider over here a system. Right? And over here there is one particle over here. Right? The this particular mass over here. Let's say that this mass is nothing but equal to m. Right? A small particle over here. It has a mass of dm, which is now going to join with the system over here. Right? And what is the velocity with which this one is moving? Let's say that it has a velocity of let's say it has a velocity of v. Okay? This dm over here has a velocity of v, let's say, where v is greater than u, let's say. Okay? So therefore, after this particle joins the system, right? Now we can imagine how the situation will be, right? There will be a small increase in the mass of the system. Will be m plus dm, right? And there will be a small increase in the velocity of the system, which is u plus du. Right? Earlier it was u, now this small mass added kind of pushes the system more. Small increases there. Right? So now what we can do, taking the whole thing as taking this entire entity as a single unit. The external force acting on it is zero. Let's apply the conservation of linear momentum. Okay. So what is the initial linear momentum? We can write dm into v plus mu is equal to, finally it is m plus dm multiplied by u plus du. Okay. Let's open up the bracket. What do you get? Mu plus mdu plus dmu plus dmdu. Fine. And on this side you have dmv plus mu. Let's remove the terms. What can we remove? Mu. Fine. And this term over here, dm into du. Now this is a very small term over here compared to the rest. Dm mass itself is small, du is even small. So over here you would be having how much is neglected over here. Fine. In comparison to the others. Fine. So now what does it become? Your dm into v minus of u. On this side what you have m into du, let's say. Fine. And now what we can do is divide. We will now divide over here. What do we divide? Divide by dt on both the sides. Okay. So if you divide by dt on both the sides, this attachment is taking place in a small interval of time called dt. Okay. So therefore, what is this du by dt? Is it the final velocity minus the initial velocity divided by the time taken? Can we call it as the acceleration at this instant? Yes. And what is the dm by divided by dt? Is it not the rate at which the mass of the system is changing? The final mass is m plus dm, the initial is m. So change in mass, final minus initial divided by the time taken, into what is the v minus u. V is the velocity of the particle minus the u is the velocity of the of the m mass, and this is nothing but the relative velocity. And we call it a v relative. It's not u relative, it's v relative of what and what, of the particle which is either entering the system or it is exiting the system, and of the particle which is relative to whom, relative to the system. Fine. So therefore, this quantity over here, since this is nothing but the net force acting, and therefore we'll argue over here that this is nothing but the force because of which the m is experiencing some amount of acceleration. And so therefore over here we will argue that this quantity is also known as the thrust force. We'll write it as F thrust. And F thrust is nothing but equal to mass into acceleration. Okay. Let's take some example on the same. Yeah. What example shall we take? What example shall we take? Okay, let's see. Suppose that you have over here some cases, right? Rain is falling over here. Fine, rain is falling over here, and case number one, case number two. Fine, let's take these two cases. Right. So let us say that in both the cases, the rate at which the mass is changing of the system is the same. Let's say first case dm by dt is positive. Second case, the sand is leaking out over here from the system. Fine. Okay. With mm, it's, it is just leaving the system. And you can say that it's being released, right? Yeah. So we want to find out how the velocity changes with time. Fine. And the rain has a velocity in this direction of, let's say, v naught. This way it is. Fine. And the rate of increase of mass is equal to mu kgs per second, and over here it is mu kg, a decrease in the mass, right? Clear it is changing of mass is also mu. What do you want to find the number one, the thrust force is how much. Number two, what is the velocity as a function of time? Fine. Okay, let's take the first case. So these particles which are hitting, and we will have to take the initial mass of this system over here, right? Let's say that initial mass is nothing but equal to capital M, and as time passes, the mass will keep on increasing over here. Right? And the initial velocity over here is v naught. Oh, that v naught we already gave. Okay, so let's say that initial velocity is, let's say it is v1 at time t0. Fine. And rate of increase of mass is a constant value. Fine. Oh my god, so much shouting there. Okay. So now we'll say that first let's find the thrust force. Okay. So what is the thrust force? Expression for that is given as dm by dt into v relative. V of the particle minus the velocity of the system. Fine. What is the v of the particle? It's v naught in minus j cap, right? Minus what is the velocity of the system at any instant of time? It is v in I cap, correct? It's a variable v it is. Fine. And we want to find the velocity, right? We notice that the velocity will change only in the x direction. We are not interested in the y direction. In the y direction, there will be other forces over here, the normal, and there will be mg that will balance. Fine. So our interest is on the x direction mode. So let's write what is the component of the thrust force along the x direction. So we will write over here that it's dm by dt into minus v in I cap. That's all. This is the only force which is acting. Dm by dt is the rate of change of mass, which is mu. So mu into minus v. So if this is the thrust force, we want to find the velocity, right? So therefore, let's write it as ma itself. So on the cart, net force is equal to ma. So therefore, how much is that? Mu minus v I cap is equal to m into a. Is a not the same as dv by dt? Yes, it is. And what is m over here? M is the rate at which the mass is changing, right? Oh, sorry. dm by dt is the rate at which the mass is changing. M is the mass of the system, the cart plus the water collected at any instant of time. So we'll write it this way: that's the dm by dt itself is equal to mu, which is a constant, which means the dm is mu dt, which is nothing but you integrate on both the sides. At time t0, the mass was given to a capital M. At any instant of time, the mass is small m. So m minus m naught is equal to mu into t, which means that m is nothing but m naught plus mu t, and you can also directly write this, since the dy by dx, whenever it's a constant m, y will be mx plus c. C is the intercept, that is at x equal to 0, the value of y. Fine. So this is nothing but y, this is nothing but mx, this is nothing but the value of y when x is 0. So therefore, now let's substitute this m over here, where this m will put it over here. Okay. It's all very simple. It is very, very effortless and simple. So therefore, we will write that mu. Now you remove the minus I cap, you remove the I cap and the vectors over here. So it becomes this vector that we just now added, that we are going to remove. Fine. M is m naught plus mu t into dv by dt. Shift the dt on the one side. Variable separation. Let's do that. Mu minus dt m naught plus mu t is equal to how much? Dv, right? Now dv by v. Now let's integrate this one. On integrating this, what do you get? At time of t0, what was the velocity given to us? I think we took it as v1, right? Yeah. Yes, initial velocity is v1. At any instant of time, the velocity is v. So therefore, this becomes natural log of v by v1. On this side, what do you have? Minus mu. This one will be natural log of n naught plus mu t, limits from 0 to t, which means what will we be having? natural log of v by v1, upper minus the lower by m naught. Okay. So, right, wasn't there one? Yes, if you integrate this, you will have to also include this constant over here, right? The coefficient of t, 1 by mu, you have to write that. Right? So 1 by mu, that we have to put over here, which means you'll get final equation as minus natural log of m naught plus mu t by m naught. So you get v by v1, it's m naught by m naught plus mu t. There is another way to do the same. Is there is another way. Initial by balancing the momentum in the x direction of the particles finally as well as the initial system. That also can be done. We'll check that also. Right. So we get v as how much? v1 m naught by m naught plus mu t. Okay. This one is clear, no doubts are there. Okay, this was one example. What about the second one? The problem here is what is the relative velocity between the particles which are just leaving and just before? Don't they have the same velocity? So there is no relative velocity, which means there is no thrust force. There is no thrust force. If there is no thrust force, then what is the what is the acceleration? No thrust force, no acceleration, which means that this cart will move with a constant velocity. For all time, it will be the same, and that's all. This part is clear. Yes, the thrust force, because the v in this direction, the component of v in this way is 0, and v relative anyway is the same of the system over here and the particles over here. No v relative. Fine. Okay, so this is done. Okay, let's take another example. Achha, we said there is another method to. Yes, there is. There is. Okay, so let's just observe. This is the system over here, right? It has a velocity, it has a mass, and these particles, they have a velocity of 0 initially. Fine. After they hit or combine with the system, now the velocity is v, and now these particles over here, all of them will have the same velocity. The mass of the system is how much? Small m it is. So what we can do is apply the conservation of linear momentum directly also, and say that the final momentum is nothing but the initial momentum, and this m over here is nothing but m naught plus mu t into v. It's nothing but m naught v1. Get v value as m naught v1 by n naught plus mu t. I hope you enjoyed today's video. Yes, if you remove the background noise, this video was amazing. Excellent. That's it for today.